Every year, thousands of miles of new railway tracks get laid down all over the world. But the Japanese, they've turned it into a true art form. Here, rails the length of a football field are born from the molten lava of steel, reaching over 2,700 degrees Fahrenheit. They're joined together to seem absolutely endless, and the concrete track slabs, as thick as 2 footballs, hide the secrets of eternity and speed. So how did the Shinkansen engineers manage to achieve that almost perfect, smooth ride? An average delay of just 36 seconds and speeds of up to 200 miles per hour? Watch till the end, and you'll find out something you'd never have guessed. We're stepping into a massive Japanese steel mill. The atmosphere is thick with heavy air, a mixture of heat, steel, and the deep hum of powerful machinery. In front of us is the main star of the show, a steel-making furnace the size of a 5-story building. It looks like the tongue of a volcano, glowing a dazzling white hot. Inside is a boiling mixture of iron and carbon. Its temperature is over 2,700 degrees Fahrenheit. The molten metal pours out with a roar into special molds, like a bright orange river of lava flowing down a mountain. The workers look absolutely tiny against the backdrop of the huge machines. After the steel is melted in that huge furnace, it gradually starts to cool, turning from a liquid into a solid but still very hot piece of metal. This piece, think of it as a thick, hot bar several feet long, is then fed into a rolling mill. A rolling mill is a gigantic machine, kind of like a huge meat grinder, only instead of a blade, it has heavy steel rollers that press and stretch the metal. The dull roar gets even louder as the machine grabs the red-hot blank. With a sound like a deep groan and the scrape of friction, the hot metal begins to stretch out, like dough for pasta, but not soft, dense and heavy. Gradually, this bar becomes longer, thinner, and more uniform, and eventually, it transforms into a long rail, 320 feet in length. That's like a football field and then some. The surface of a rail like this has to be perfectly smooth, without the slightest ripple. Because if it's even a little bit uneven, the high-speed Shinkansen train won't glide smoothly over it. It'll start hopping at the joints, like a little frog in a swamp. After rolling, the rail is still incredibly hot. Steam rises from it, and you can hear a crackling sound, like when water hits a hot stove. But this is almost its final form. Long, heavy, smooth, ready for inspections, grinding, and its future. Becoming part of the track for one of the fastest trains in the world. To reduce the number of joints, which are potential spots for wear and noise, Japan uses a method of continuous welded rail. That's when several rails are joined into one incredibly long strip, almost 5,000 feet long, making the rail seem endless. Welding rails for high-speed trains like the Shinkansen is a high-precision technological process. The goal is to turn individual rail sections into a single, seamless strip up to almost a mile long. It's this type of connection that lets them avoid the traditional clickety-clack sound when going over joints, reduces wear, and creates that smooth gliding effect. The welding process happens in several stages. Most often, they use thermite welding, a reliable and pretty spectacular technology. 2 rails are placed end to end, so a gap of a few millimeters is left between them. The surfaces of the future joint are thoroughly cleaned of rust, scale, dust, and any other contaminants. It is crucial that the edges of the rails are perfectly even, like knife blades before being joined. Next, a special mold made of a sand mixture or a heat-resistant material is mounted around the joint. It holds the molten metal during the reaction and gives it the required shape. A thermite mixture, a powdered mix of aluminum and iron oxide, is poured into a small container above the joint. When it's ignited, a reaction occurs, during which a temperature of over 4,500 degrees Fahrenheit is released. As a result, molten iron is produced, which flows down and fills the gap between the rails, joining them at a molecular level. The reaction takes several minutes. During this time, you can hear hissing and crackling, and a bright flame rises above the joint. It looks just like a miniature volcanic eruption. After the metal solidifies in 10 minutes, the mold is removed, and the excess metal is trimmed off. The joint is then ground to a perfectly smooth surface, so the train wheel doesn't feel the transition from one piece of rail to another. The finished joint is checked with laser measurements, as well as with ultrasonic sensors that look for any possible microcracks. A rail like this is installed as a single, solid block and has a minimal number of service points, which lowers repair costs and the risk of delays. In a world where every second is precious, Shinkansen engineers discovered the secret to eternity: slab track. Instead of traditional stone ballast that crumbles under the pressure of time, they created monolithic giants out of concrete. These titan-like slabs reach a thickness of 26 inches. That's the height of 2 footballs stacked on top of each other. The Japanese masters came up with a genius solution: encapsulation elements. Imagine a metal cradle that hugs the rail like a mother holding a child. These cradles not only hold the steel guides, but also isolate them from vibrations and electricity. It's like giving the rails superpowers, the stability of Superman, and the flexibility of a dancer. The most genius part of the whole system is what you can't see. Between the concrete slabs and the foundation, the Japanese placed resilient layers that act like giant shock absorbers. In tunnels, slab track works true wonders of economy. A lower track height means a smaller tunnel cross-section, which reduces construction costs by a fantastic 30%. Transporting the sleepers to the installation site is done in several ways, depending on the distance and accessibility. Transporting sleepers by road requires special measures to prevent any movement during transit. Transporting sleepers by rail must be carried out according to a loading plan approved by the railway department. For short distances, special trucks with cranes are used. For long routes, railway flat cars are used. Safety during transport is critical. One concrete sleeper must be lifted by 4 workers, which highlights their significant weight, approximately 165 pounds per worker. For mechanized lifting, special grippers and cranes are used to avoid damage to both the sleepers and the workers. At the construction site, the installation process begins with preparing the foundation. For slab track, which is primarily used on the Shinkansen, the sleepers are installed on pre-prepared concrete slabs. Each sleeper is positioned with an accuracy of 1/4 of an inch, since even minimal deviations can cause problems at speeds of 200 miles per hour. The installation is carried out by specialized crews using precision equipment. First, support points are installed every 2 feet, the standard interval for high-speed lines. Each sleeper is attached to the base with special 1-inch diameter anchor bolts, which are driven 6 inches deep into the concrete slab. The process is complicated by the need to integrate with the power supply and signaling systems. The sleepers have special channels for laying cables, as well as insulators to prevent short circuits of the traction currents. Installers must consider the location of all engineering systems, including drainage channels and grounding. The final stage includes installing vibration isolation pads between the sleepers and the foundation. These rubber steel elements significantly reduce the transmission of vibrations from the trains to the surrounding structures. After the installation is complete, the entire section is tested by a special measuring train that moves at speed and records the slightest deviations in the track's geometry. Even with over 120,000 trains running on the line each year, the average delay is just 36 seconds. Over half a century, the speed has increased from 130 miles per hour to 200 miles per hour, and the passenger flow is now 1 million passengers a day. A new line is expected to be operational at a speed of 310 miles per hour, with an estimated travel time between Tokyo and Osaka of 67 minutes. Construction began in 2011, was initially planned to open in 2027, but is now postponed until at least 2034. Every hour, over 3,000 miles of electrical cables are laid worldwide. But few people know that this involves gigantic metal spools, each one an engineering marvel weighing over 20 tons. Their diameter can reach 33 feet, and inside, up to 37 miles of wire capable of transmitting hundreds of thousands of volts. A half-inch error, and everything goes down the drain in losses. How are these steel giants created with precision down to 1/100th of an inch? And why can't any power transmission line exist without them? Watch, and you'll be amazed. This story begins with calculations. Before the first bolt touches the steel, a team of engineers dives into mathematical alchemy. Each spool for a high-voltage power transmission line is created for a specific type of cable, so there are no trifles here. Blueprints, models, and calculations come into play. It is necessary to consider the outer diameter of the cable, for example, 2 inches. Its weight, which can exceed 3 pounds per foot. Density, number of turns, winding angle, and even the insulation's coefficient of friction. On average, up to 6 miles of cable are wound onto one spool. That's almost 32,000 feet of heavy, multi-insulated wire that, under voltage, can carry hundreds of thousands of volts. An error of just half an inch in the spool's diameter, and the cable might start coiling incorrectly, shifting, compressing, overheating. In the worst case, it gets damaged even before installation. And that's tens of thousands of dollars in losses before even starting. Moreover, the core diameter of the spool can reach 5 or 6 feet, and the total diameter of the flanges up to 33 feet. The weight of the structure exceeds 40,000 pounds. That's like 2 large SUVs screwed together and stood upright. And this entire mass has to rotate smoothly, without misalignment or vibrations. Are you impressed? Because I sure am. To avoid disasters, engineers add a coefficient of material expansion. As metal changes size when heated, consider transport weather conditions, and also the winding geometry, because even too steep a winding angle can damage the cable when it's unwound. When the drawings are approved, giant workshops come onto the scene, hangars the size of a football field. Here, metal flanges, cores, and frames appear. Most often, the spools are made of steel. It's steel that can withstand the weight of the cable and the loads during transport. For an average spool, more than 2 tons of steel are needed at the laying site. So, each giant spool for power transmission lines starts with cold metal, thick steel sheets that arrive at the factory as plates measuring 6 by 12 feet or more. Their thickness ranges from half an inch to 1 inch, and this steel is structural. Strong, tough, capable of withstanding high loads without cracking or deforming. First, the sheets are fed to plasma or laser cutting machines, which are programmed according to precise drawings. A giant plotter, emitting a hot beam, literally burns complex shapes into the metal. These machines operate with an accuracy of 1/100th of an inch. Such precision isn't for beauty's sake, it's critical. Because even the slightest error on one flange can cause the spool to lead the cable off-center during rotation. And that's a risk of misalignment, jamming, and failure during installation. The discs for the flanges are cut in pairs, identical rings 20 to 33 feet in diameter, with holes for connecting bolts. Technical slots and markings for future reinforcing elements are made on the surface right away. After cutting, they are processed by grinding machines. Burrs are removed, and they are prepared for welding. At the center of the future spool is the core, a large steel pipe that will serve as the drum for winding the cable. Usually, its diameter is from 5 to 8 feet, and its length up to 10 or 16 feet. The pipe is cut from thick wooled rolled stock and reinforced with stiffening ribs inside. These are thick steel strips that form a frame and prevent the pipe from sagging under the weight of the cable. After all the parts of the future spool are cut, the stage where every millimeter matters begins: welding and assembly. Here, metal geometry transitions from 2-dimensional to 3-dimensional. 2 giant flanges are attached to both sides of the core. A steel pipe that will hold tens of thousands of feet of heavy cable. The entire structure must withstand not only its own weight, but also dynamic loads during rotation and transport. Welding is done manually or automatically, depending on the size and complexity. Most often, submerged arc welding is used, which allows for creating dense, strong seams without voids. The joints are additionally ground, as any protrusion or unevenness can damage the cable during winding. Then, reinforcement. Stiffening ribs, which are thick steel plates placed inside the core and at the joints with the flanges, are added to the structure. They prevent deformation under pressure. To fix all the parts, bolts up to 1.5 inches in diameter are used, tightened with special hydraulic torque wrenches. One such bolt can withstand a load of tens of thousands of pounds. The finished spool is installed on a temporary axle and rotated. Engineers check the balance using a laser level, ensuring that during rotation, no part shifts even 1/4 inch. If the structure wobbles, it's ground, adjusted, and sometimes parts of the elements are reassembled. And only after this is the spool considered ready for the final stage: anti-corrosion treatment, painting, and testing. The finished spool has just been removed from the rotating stand after welding. It's still warm, smells of metal and ozone, and its surface is covered with dark gray spots. That's scale. It looks like a thin crust, similar to coal dust, and remains after the metal comes into contact with high temperature. Along with it, small remnants of oil, dust from grinding, handprints. Painting in this state is a waste of time. The coating won't stick, it will peel off in the first few months. So first, mechanical cleaning takes place. The workshop buzzes with tools. Workers with stiff brushes on grinding machines go over the joints, flanges, and stiffening ribs. They remove rough irregularities, clean the seams of residual slag. But this is not enough. Next, a sandblasting unit comes into play. A large chamber, or just a separate section in the workshop. The spool is brought inside on a special platform. Then, the roar of a compressor and a stream of fine abrasive starts hitting the steel surface under high pressure. Sometimes quartz sand, sometimes steel balls. It sounds like a storm of hail hitting tin. The surface changes before your eyes. Where there was just dark mottling, now there is an even, matte gray metal with a slight roughness. If you run your finger over it, you feel not smooth, but slightly velvety to the touch. This is exactly what's needed, because this micro-roughness significantly improves adhesion with the anti-corrosion primer. In chemistry, this is called the anchor profile effect. When the treatment is complete, the entire surface is blown with air, blowing out residual abrasive from corners and crevices. This is the perfect moment to apply an anti-corrosion primer, the first protective barrier between the metal and the environment. A worker in a mask and protective suit takes a sprayer with a thick gray liquid, a zinc-rich primer. With each press of the trigger, a thin, even mist comes out of the nozzle, settling on the surface. The zinc in the primer acts as a sacrificial metal. It is the first to react with moisture, saving the steel from corrosion. After a few minutes, the spool is already covered with a thin, almost invisible layer. It looks a little lighter, as if dusted. In a few hours, this primer will polymerize and form a chemically resistant film that is firmly bonded to the metal. It is this layer that takes the first hit from time, moisture, and temperatures. For export or harsh climatic zones, additional layers may be applied: marine varnish, hydrophobic films, or even heat-resistant coatings that can withstand heating up to 300 degrees Fahrenheit. When the coating dries, the spool is carefully inspected. Under ultraviolet light, all microcracks, bubbles, or gaps in the layer are visible. If there are doubts, an electric spark test is performed. A special probe glides over the surface, and a spark jumps only where the insulation is compromised. This ensures that every inch of metal is reliably protected and will withstand years of operation in any conditions. Did you know that the machines powering global industry, transportation, and our electrical grids consume energy equivalent to building thousands of the Great Pyramids of Giza every single day? This hidden power isn't just about raw force. It's delivered by some of the most massive and awe-inspiring engines ever conceived. From the dawn of the industrial age to today's modern world, engineers have chased the dream of bigger, stronger, more efficient powerhouses. Get ready to take a journey through history and dive into the incredible scale and engineering genius behind the world's most powerful and giant engines. Our journey begins in the age of steam, a time when raw pressure was king. Picture the late 18th and 19th centuries. The engines that drove the Industrial Revolution weren't small. Early steam engines were clunky, but they quickly grew into colossal machines. Think of the beam engines, towering structures in factories and mines, with massive beams rocking back and forth, driving pumps and machinery with the power of boiling water. These were mechanical giants, their sheer physical size necessary to contain the immense forces of steam pressure. As steam technology evolved, so did the engine's power and scale. Reciprocating steam engines became the heartbeat of global shipping. Imagine the engine room of a massive early 20th century ocean liner. You'd see multi-cylinder engines with pistons the size of trash cans, connecting rods like tree trunks, and crankshafts so large they needed multiple men just to inspect them. These engines were colossal, spanning multiple decks, their rhythmic pounding driving propellers powerful enough to push thousands of tons across vast oceans. They were engineering marvels of immense moving parts, powered by the simple expansion of steam. While steam dominated for a long time, the early 20th century saw the rise of a new kind of giant, the diesel engine. Unlike external combustion steam engines, diesels burn fuel directly inside the cylinder. This was a game changer for efficiency and power density. Early large diesels quickly found their way into ships and power generation. Imagine a large, slow-speed marine diesel engine built for a cargo ship. These engines are absolutely colossal, often standing as tall as a multi-story building and stretching the length of a gymnasium. Modern marine diesel engines, like some built by Wärtsilä or MAN, are among the largest machines on Earth. The biggest ones have multiple cylinders, each with a bore, diameter. Wider than a grown man is tall. Their crankshafts are multi-piece monsters, weighing hundreds of tons. These engines produce over 100,000 horsepower, enough to move supertankers and container ships carrying 20,000 containers. The sheer scale of these components, pistons, connecting rods, crankshafts, cylinder blocks, is mind-blowing, a testament to achieving immense power and torque from internal combustion. As technology advanced further, especially in the mid-20th century, the gas turbine emerged as another powerhouse. Unlike diesels or steam engines that use pistons, gas turbines burn fuel to create hot gas that spins a turbine wheel, similar to a jet engine. While aircraft engines are built for power to weight, industrial and power generation gas turbines are built for sheer output. Imagine a power plant gas turbine the size of a bus or even a small house. Modern industrial gas turbines, like those in GE's H-class, are engineering marvels generating hundreds of thousands of kilowatts, enough electricity for hundreds of thousands of homes from a single unit. They involve incredibly complex internal components, spinning at thousands of revolutions per minute in temperatures hotter than molten lava. Their power output, efficiency, and relative compactness compared to older technologies make them the giants of modern electrical generation. Some large ships, including cruise liners, also use gas turbines for their combination of power and smoother operation. Comparing these generations of giants is fascinating. Steam engines were the pioneers, relying on brute pressure and massive physical structures. Diesel engines brought efficiency and incredible low-end torque, dominating heavy transport. Gas turbines delivered immense power density and high-speed rotation, becoming the backbone of modern power grids and high-speed applications. Each technology pushed the boundaries of materials, science, and engineering to harness energy on an ever-increasing scale. These engines, whether the visible, rhythmic giants of the steam age or the humming complex powerhouses of today, are the unseen heart of the modern world. They drive global trade across oceans, power the trains that move goods and people, generate the electricity that lights our cities and runs our factories, and fuel the massive pumps and machinery of heavy industry. They are a testament to humanity's relentless drive to build bigger, stronger, and more powerful machines. So, the next time you see a massive cargo ship, a powerful train, or simply flip a light switch, take a moment to remember the incredible journey through history and the engineering genius behind the world's most powerful and giant engines. From towering steam engines and colossal marine diesels to blazing hot gas turbines, they are the hidden giants that built our modern world. What era or type of giant engine fascinates you the most? Let us know in the comments. Every year, the world produces over hundreds of millions of artillery shells, complex and precise items that play a key role in modern armed forces. From the smallest shells to heavy 6-inch casings, each one goes through a complex path, from metal scrap to a powerful munition capable of changing the course of a battle. Huge factories work continuously, using the latest technologies and high-precision equipment to provide armies worldwide with reliable and effective weapons. In this video, we will delve into the process of manufacturing artillery shells. From metal processing and forming the casings to filling with explosives and testing the finished product. Get ready to see how millions of tiny details turn into a formidable weapon and understand why this is so important for the security and defense capabilities of countries. Don't miss it. It will be spectacular and extremely interesting. The production of artillery shells begins with the selection and preparation of the metallic material. The basis for most shells is high-quality steel, which provides the necessary strength, heat resistance, and accuracy. Metal for blanks is usually supplied in the form of large rolls or sheets, with thickness ranging from a few tenths of an inch to several inches, depending on the caliber of the shell. In the United States, annual steel production is approximately 87 million tons, or about 96 billion pounds. From this enormous quantity, a certain portion goes to the defense industry, where the metal undergoes strict quality control and certification. For example, Special alloy steel is used for artillery shells, which has increased strength and corrosion resistance. Blanks for shells are made at steel mills, where the metal is melted in large furnaces at temperatures exceeding 2,700 degrees Fahrenheit. After this, the molten metal is poured into molds, resulting in large plates or rectangular blocks. Then these plates are rolled on rolling mills, reducing the thickness to the required parameters, 2 inches and less. Rolling mills can be either hot or cold, depending on the processing stage. Hot rolled sheets have lower accuracy, but are easily formed, while cold rolled sheets are ideal for parts requiring high precision and a smooth surface finish. Next, the metal sheets or rolls are transported to munitions plants. Here, using equipment, the shell casings are cut from the blanks, tubular or cylindrical, depending on the type of munition. In 1 hour, a modern facility can process hundreds of thousands of pounds of metal, transforming it into hundreds of finished casings. To understand the scale, in 2022, the United States manufactured over 10 million artillery shells of various calibers. Considering that one shell casing weighs about 100 pounds, producing this quantity required over 1 billion pounds of special steel. Blanks arrive at the munitions plant, where their transformation into actual shells begins. Heavy spools of steel or other alloy, weighing several tons and stretching hundreds of feet long, are placed on special uncoiling platforms. These setups unwind the roll like a giant spool, feeding the steel strip further down the line. In the next stage, high-precision guillotine shears or rotary disc cutters are used to cut sheets or discs of precisely specified length and width from the roll. For shells of different calibers, from less than an inch to 6 inches, different sized blanks are needed, so the computer numerical control system adjusts the cutting parameters to the required standard. Next, the blanks are heated in industrial furnaces to a temperature of approximately 2,000 degrees Fahrenheit. The metal becomes plastic, like clay. It is transferred to hydraulic presses, where, under pressure of hundreds of tons, the future shells are given their initial shape, an elongated cylinder with a pointed end. After the metal blanks have undergone initial forming, usually by deep drawing or hot stamping, they are still far from ideal. The blanks come out slightly deformed, with excess length, an uneven edge, and micro bends. Therefore, the next stage is calibration and trimming. The hot part cools in special baths or under a stream of air, so the steel sets in its new shape. Then the shell is fed to a trimming machine. Rotating blades or milling cutters cut off the excess length. For example, for a large artillery shell, the typical casing length is 15.6 inches. This is accuracy not by eye, but to the thousandth of an inch. After this, the part passes through a calibrating unit. This is either crimping rolls or boring systems with precision micrometers. The casing diameter must match the standard plus or minus 0.001 inch. Otherwise, the shell will either not enter the gun's chamber or will get stuck. At the output, we have a part ready for further processing, with clear geometry and parameters. The blanks slowly move inside the computer numerical control machines. Massive machines with gleaming tools rotating at speeds up to 15,000 revolutions per minute. Sharp milling cutters, resembling miniature circular saws, cut off excess metal with surgical precision, as if engraving the steel cylinder. Under the automatic aim, the location for the rotating band, a narrow groove that holds a copper ring, thanks to which the shell moves along the rifling of the gun's barrel. Then, threading for the fuse. The supply of coolant is accompanied by hissing and steam, sparks, steel, fog. Every turn of the tool transforms a formless blank into a high-precision shell. After milling, the shell casings are sent to the heat treatment stage. And this is, without exaggeration, a fiery forge of high technology. The blanks are submerged in furnaces where the temperature reaches over 1,600 degrees Fahrenheit. In a dark hall filled with the orange glow of the metal, giant furnaces heat the casings to a state where the steel becomes more flexible, loses stress, and acquires the necessary strength. After heating, rapid cooling. This is either an oil bath, streams of air, or water quenching. The choice depends on the type of alloy. The process is called hardening, and it's what transforms the shell casing from a simple blank into steel capable of withstanding the immense stress during firing. Next, grinding. Each casing passes through machines that, with a screeching sound, remove microns of remaining scale, irregularities, and excess material buildup. Streams of coolant create a mist, and the air smells of metal and machine oil. Workers in safety glasses carefully monitor each casing so as not to miss any micro cracks or deformations. After grinding, it's time to move on to the most important part, creating the explosive filling. Before this, the casings go through a degreasing and inspection stage again. Not a speck of dust or a drop of oil should remain inside, so as not to affect the stability of the explosive material. A component is installed in the rear part of the shell through which the charge will later be introduced, or it is sealed immediately if the design requires it. If it's a high explosive shell, the casing is filled with explosive material, usually TNT, octol, or a mixture like Composition B. The process can be casting, where molten explosive is poured into the casing, or pressing. This is an extremely delicate and controlled process. Everything happens automatically, with remote control and under the supervision of specialists in armored cabins. A socket for the fuse or the fuse itself is inserted into the nose part of the shell, either immediately before use or during manufacturing. Everything is sealed to prevent moisture from entering. In the final stage of manufacturing, artillery shells enter the paint booths, large rooms with exhaust fans, filters, and automated sprayers. Here, the shell casings are covered with a special paint that not only marks the type of munition, but also protects the metal from corrosion during storage or transport. The color matters. Yellow, for high explosive fragmentation; green, for smoke; black, for armor piercing; and blue often indicates training rounds. The paint is applied evenly, in a thin layer, usually in several passes, so as not to exceed the permissible weight of the shell. After drying, marking follows: caliber, shell type, serial number, batch number, production date. This is done with a stencil or using an industrial printer. Every detail matters. Military personnel need to quickly identify exactly what they have in front of them, under what conditions it can be used, and from which batch it came. Every year, the world produces over 60 million metric tons of aluminum, and a significant portion of this metal is turned into key parts for automotive engines. Did you know that over 75% of modern engines have aluminum cylinder heads? This choice isn't accidental. Lightness, strength, and the ability to withstand high temperatures make aluminum an ideal material. But what happens behind the scenes in the production of these critical components? How are tons of metal transformed into complex, high-precision parts? Today, we're diving into the fascinating world of industrial manufacturing, and we'll show you the whole journey, from raw material to finished cylinder head. Cylinder heads are most often made from two primary types of materials: aluminum alloys and cast iron. As of 2025, over 75% of modern automotive engines are equipped with aluminum heads, due to their lightness, good thermal conductivity, and the reduction of the overall weight of the power unit. One aluminum cylinder head assembly weighs on average between 10 and 20 pounds, whereas cast iron equivalents can exceed 40 pounds. Aluminum for such parts isn't just metal, it's a high-quality alloy, for instance with added magnesium or copper, which provides strength at high temperatures. The main suppliers of aluminum are countries like the People's Republic of China, which provides over 60 million metric tons annually, and India. In the United States, the majority of aluminum raw material is supplied by sea transport in the form of ingots or granules, which are subsequently remelted at local foundries. One standard 20-foot container holds up to 48,000 pounds of aluminum ingots, which is enough to produce over 1,000 heads. Cast iron, although less popular in new engines, is still actively used in heavy machinery and trucks due to its durability. Its production requires components: iron ore, coke, and limestone. The United States partially extracts ore itself, but imports a significant portion from Canada and Brazil. Rail transport is used, One typical train with raw materials can deliver 10 to 15,000 tons of iron ore to metallurgical plants. After the materials arrive at the facility, they undergo cleaning, sorting, and melting. For example, casting one cylinder head requires up to 22 pounds of aluminum, and the cycle from melting to cooling takes about 90 minutes. This is just the beginning of the production chain, in which each part goes through dozens of stages before being assembled onto an engine. Aluminum ingots or granules arrive at the plant in sealed containers. They are unloaded onto special platforms with automated cranes and delivered to the melting shop. Before melting, the aluminum is cleaned of impurities and moisture to avoid porosity in the finished casting. For this, the raw material is placed on vibrating tables with metal detectors or sorting conveyors. Robots or operators manually or mechanically reject unsuitable material. This is how contaminants, paint, oil, plastic, and shavings of other metals are identified. Thanks to quality cleaning of aluminum before melting, the rejection rate is reduced by 60 to 80%. The storage temperature for the raw material is controlled, about 70 degrees Fahrenheit, to avoid condensation, which can cause microbubble explosions if it gets into the molten metal. After cleaning from moisture and impurities, the aluminum is fed into large melting furnaces. These can be gas or induction units that heat the metal to approximately 1,220 degrees Fahrenheit. A stable melting temperature is maintained in these furnaces thanks to automated control systems, which prevents overheating and preserves the homogeneity of the future alloy. Furnaces typically have a volume of 5 to 10 tons, and one such furnace can produce up to 300 or even 500 cast cylinder heads per shift. One shift lasts 8 or 12 hours. The production flow is set up so that the molten metal is continuously supplied for casting, so even 15 or 20 minutes of downtime can cost the enterprise thousands of dollars due to lost pace and cooling of the material. Alloying elements are added to the molten aluminum, primarily silicon and magnesium. These elements increase the strength, heat resistance, and wear resistance of the finished part, making it suitable for operation under high pressure and fluctuating temperatures in the engine. As you can see, magnesium doesn't just improve human strength and wear resistance, but aluminum's too. After adding impurities, the alloy necessarily passes through a ceramic filtration system. Special porous filters capture oxides, microscopic particles of slag, and residual impurities. Without this filter, slag could get into the mold, form microcavities in the part's structure, and reduce its lifespan by tenfold. Filtration usually occurs in the ladle or holding furnace, where the molten metal is transferred from the main furnace. This is an intermediate stage where the metal is again stabilized by temperature and checked for chemical composition using spectrometers to precisely match tolerances. After cleaning and filtration, the molten aluminum goes to the casting shop, where it is poured into molds, a key moment when hot metal turns into a specific part, the cylinder head. This process must be extremely precise because the mold is complex, with numerous channels and cavities, and the engine's performance depends on the casting quality. Most often, gravity die casting or high-pressure die casting are used for head production. In the first case, the molten metal flows by gravity into a metal mold that can withstand several thousand cycles. In the second, the molten metal is injected under pressure up to 10,000 psi. Ensuring precise filling of even the smallest channels. The mold, made of high alloy steel, is preheated to 400 degrees Fahrenheit or more to avoid thermal shock. The metal is supplied from a ladle or through an automated continuous feeding channel. A venting and gating system ensures air displacement, otherwise voids will form. The metal cools in the mold for 30 seconds to 1.5 minutes, after which the mold opens and the casting is sent on for further processing. Modern lines are equipped with sensors for temperature, pressure, and filling. The control system monitors the volume of molten metal, feeding speed, mold temperature, and metal temperature in real time. A deviation of more than 2%, and the machine automatically rejects the blank or adjusts the parameters. One casting station produces 40 or 60 heads per hour, depending on the technology. After the casting and cooling of the metal are completed, the next stage begins, removing the head from the mold. If sand casting was used, the mold is broken, It's a single U structure made of a sand-clay mixture, so it's simply broken apart to get the casting. In the case of die casting, a metal mold is used, which automatically opens, and the part is ejected by special pushers. At this stage, the so-called gray or rough blank is obtained, an unprocessed head with gates, risers, and irregularities. Its weight is 10 to 20 pounds, depending on the engine type and design. Almost immediately after removal, the heads are often sent for heat treatment. This typically includes quenching and tempering. The process involves heating to 1000 degrees Fahrenheit, holding at that temperature, and controlled cooling. This strengthens the metal structure, increases hardness, wear resistance, and thermal stability, critical parameters for operation in the engine's hot zone. After heat treatment, the cylinder head proceeds to the computer numerical control machining stage. The head is secured on a fixture in a multi-axis machining center. A computer program precisely sets the coordinates, speed, and order of processing. Machining includes milling the mating surface to the engine block, drilling holes for bolts and other parts, boring channels for coolant and oil, forming valve seats and guides. One machining center can complete a full cycle in 10 or 25 minutes. Every minute in the United States, over 1,000 feet of copper pipe is manufactured. But behind this seemingly simple component lies large-scale production, explosive temperatures reaching 2,000 degrees Fahrenheit, and even espionage investigations. From molten lava in furnaces to laser marking under ultraviolet light, each pipe follows a journey straight out of a movie about industrial superheroes. And did you know that some people are audacious enough to counterfeit copper just by painting its surface? This story is about how real pipes are made and how to distinguish the genuine article from a dangerous fake. Let's dive into a world where every second equals a ton of metal. It all begins underground, in the copper mines of Arizona or Montana, where hundreds of thousands of tons of copper ore are extracted each year. It's crushed, washed, purified, and the output is shiny granules of pure copper. These granules go into smelting furnaces, where temperatures exceed 2,000 degrees Fahrenheit. Here, the copper transforms into molten lava. The molten copper is poured into long molds, so-called slabs, or ingots. They resemble thick orange beams, glowing white-hot. These ingots are destined to become pipes, but there's still a long way to go. Pure copper in the form of ingots or cathode plates is loaded onto railroad flat cars, trailers, or even ships, and transported to rolling mills or pipe manufacturing plants. Cathode plates are thick metal sheets, approximately 3.3 inches by 3.3 inches, weighing up to several hundred pounds each. At the plant, the ingots or cathodes might first undergo additional remelting to achieve the required purity or desired shape, for instance, round billets for pipes. Then, they are heated and sent to the rolling mills. Rolling lines operate with machines boasting over 10,000 horsepower. The ingots are sent to rolling stands, machines weighing tens of tons. Giant rollers crush the hot metal, transforming it into long strips. The sight is incredible. The red-hot copper stretches out, sparks fly everywhere, and nearby, streams of water cool the metal, turning it into a shiny, almost mirror-like sheet. In modern workshops, all of this is controlled by computers. An operator sits in a glass cabin, similar to an airplane cockpit, monitoring dozens of screens. Here, every temperature, pressure, even the sheet thickness is under control. If anything goes wrong, the automation instantly stops the line. Now for the most interesting part. The copper sheets are cut into blanks. In plants where the copper sheets are still hot after rolling, powerful hydraulic or mechanical shears are used for cutting. They look like giant guillotines with massive steel blades. The sheet moves along a conveyor. An automatic sensor determines the exact cutting spot. The blades descend with immense force and slice off pieces of the required length and width. What do I mean when I say, with immense force? Sometimes it's tens of tons of pressure. All this happens in seconds, often while the sheet is still moving. That is, the line doesn't stop, and the guillotine cuts on the fly. For certain formats or thinner sheets, rotary knives are used. These are rotating steel discs that cut the copper as the sheet moves. It looks a bit like cutting pizza, only on an industrial scale. This method is suitable for narrow strips, or when the sheet needs to be cut, not only crosswise but also lengthwise. In modern factories, laser or plasma cutters are used for complex shapes or high precision. A laser beam or plasma arc heats and vaporizes the copper at the point of contact. This results in a perfectly smooth cut, almost free of burrs. Lasers are used for non-standard parts or when special geometry is required. After the main cutting, the blanks may pass through special edge trimming machines that remove irregularities, sharp edges, or excess material. The cut blanks are fed into drawing machines. This is a huge press that draws the copper through a steel die. The output is a perfectly round, smooth pipe. All this happens in mere seconds. The machinery operates at incredible speed. At large plants, like Mueller Industries, they can produce over 1.5 million feet of pipe in a single shift. That's, no lie, like the distance from Chicago to Detroit. Each pipe undergoes automatic inspection. Laser scanners search for microcracks and defects, and special robots select samples for additional testing. After being drawn from the red-hot die, the copper pipe is still hot, flexible, and prone to deformation. To quickly give it stability, the pipes are automatically directed onto a conveyor, leading to special cooling pools. Inside is cold water, which creates clouds of steam upon contact with the incandescent metal. This sharp temperature drop locks the pipe's shape, preventing it from bending or losing its geometry. Cooling takes only a few tens of seconds, but is crucial for quality. Next, the pipes arrive at the precision cutting table. Here, they are met by automated robots equipped with cutting discs or hydraulic knives. They measure the length with laser sensors and quickly cut the pipe according to the standard. For example, 10, 20, or 40 feet, depending on the order. Cutting accuracy reaches tenths of a millimeter, and the speed is up to several hundred pipes per hour. After this, the pipes undergo quality control. Laser scanners check the external appearance, looking for cracks, burrs, or other defects. Rejected pieces are automatically sent back for remelting. Those that pass inspection continue along the conveyor to the marking machines. Here, a laser mark is applied to each pipe. It encodes the production date, batch number, sometimes even a QR code for tracking. This allows for precise identification of each pipe in case of claims or the need for quality analysis. After marking, the pipes might still be slightly damp from the cooling water. To prevent corrosion and ensure a perfect appearance, they are moved into drying chambers. These are tunnels with powerful fans and heating elements. In just a few minutes, the moisture completely evaporates and the pipes acquire their characteristic copper sheen. Next comes the packaging stage. Here, robotic manipulators come into play. They pick up the pipes using suction cups or grippers, very carefully stacking them into bundles of 10, 50, or 100 pieces, depending on the diameter and length. The robots work with surgical precision to avoid damaging the pipe surface and prevent deformation. After forming, the bundle is secured with metal or plastic straps for reliable fixation. Some plants add protective film or cardboard inserts to prevent scratches during transport. The finished bundles are automatically moved to warehouse platforms. There, each batch receives a logistics label with all the data about the manufacturer, dimensions, production date, and final recipient. Then, loading onto trucks or railroad flat cars. Everything happens as quickly as possible. A modern plant can prepare thousands of tons of pipe for shipment in a single day. Thanks to automation, this stage minimizes human involvement, ensures safety and accuracy, and guarantees that the pipes will arrive at the customer in impeccable condition. Oh right, I promised to tell you about the spy games. This is a real detective approach in manufacturing. Due to the high price and constant demand for copper, temptation arose for unscrupulous manufacturers or intermediaries. They started counterfeiting markings and passing off cheaper alloys, or even other metals as pure copper. Fraudsters became so brazen that they began forging documents and selling bootleg goods under the guise of reputable brands. Counterfeits can be dangerous. They often fail under pressure or corrode faster. A rupture in such a pipe can cause accidents, flooding, or fires. Counterfeiting scandals have occurred in many countries when it was discovered that a copper pipe actually contained only a thin layer of copper, with cheap metal inside. Manufacturers spent years building their reputations, and counterfeits under their name could lead to mass recalls and lawsuits. Therefore, pipes are now marked with invisible inks visible only under ultraviolet light. This helps combat counterfeiting. Every hour worldwide, people eat over 500 tons of popcorn. That's more than the weight of 2 Boeing 747 jets. But have you ever stopped to think that inside every single kernel, there's a miniature steam boiler that explodes with enough power to increase its size by 50 times? It all begins in ancient caves in Mexico and ends up in ultra-modern factories where hot air waves, optical sorters, and cheese powder sprayers create that perfect crunch you love. Ready to see how a simple corn kernel turns into the explosive taste of your childhood? Then don't blink. It's about to get even tastier. Popcorn is one of the oldest snacks in the world. Archaeologists have found corn kernels that could still pop in caves in Mexico and Peru, and they're over 5,000 years old. And here's a cool fact. Some of those old kernels were actually still capable of turning into popcorn in a microwave today. Can you imagine that? The first people to start eating popcorn were Native American tribes, like the Maya, Aztecs, and Incas. For them, it wasn't just a treat. Popcorn had ritual significance. They used it in ceremonies, decorated idols with it, and even made jewelry and necklaces from it. Popcorn was kind of like a gift for the spirits. Popcorn made its way to North America thanks to the local tribes, and they were the ones who introduced the early settlers to this wonder. There's a legend that at the very first Thanksgiving in 1621, popcorn was also on the table. But it wasn't until the 19th century that popcorn really started becoming popular among Americans. People used to pop it right in skillets over a fire, and then, boom! In 1885, the first street vending machine for making popcorn appeared, created by Charles Cretors. And that was it. Popcorn went out into the world. First to fairs, then to movie theaters. The Great Depression really brought popcorn its fame. It was cheap, tasty, and fun. A little bit of comfort during tough times. That's why it's still associated with coziness, entertainment, and childhood today. Popcorn isn't just regular corn. It's a special variety, Zea Mesa Verta, the only one that can explode when heated. And it all starts in the field. Popcorn corn kernels are planted in the spring when the soil has warmed up enough, usually at a temperature of at least 50 degrees Fahrenheit. Fields are often chosen in drier regions because popcorn doesn't like too much moisture, which can spoil the kernel. In the United States, the main farms are located in the states of Indiana, Illinois, Nebraska, and Iowa. The plants grow slower than regular corn, but the result is worth it. It's important to wait for the cobs to fully mature. The kernels need to be hard, with low moisture content, so they pop well when heated. After harvesting, the cobs are dried, first naturally and then in special dryers, where the moisture level is brought down to an ideal 13 or 14%. Next, the cobs are shelled. The kernels are separated from the cobs using special machines. Then, the kernels go through a sorting system. Only whole kernels, uniform in size, are selected because the quality of the pop depends on this. After sorting, the kernels are packed into bags or containers and sent to factories or processing centers, where they'll be turned into the familiar popcorn we all know. Salty, sweet, caramel flavored, or even with cheese. After harvesting, drying, and sorting, the corn kernels are transported to specialized facilities. A typical popcorn plant in the United States processes up to 500,000 pounds of kernels per week. The biggest players in the market, Conagra, Pop Secret, Act 2, have their own supply networks and completely control the process from the field to the package. The kernels arrive at the factory in trucks, carrying up to 50,000 pounds of corn at a time. The truck dumps the kernels into a receiving pit where they move along a conveyor belt to the cleaning and inspection line. A sample is taken from the batch and placed in a laboratory moisture meter. The ideal moisture level is about 14%. If it's higher or lower, the batch won't proceed, or it's sent for drying. To check the physical quality of the corn, a sample of kernels is placed in an optical sorter. It scans each kernel with cameras under bright light, and it automatically rejects kernels that are chipped, have dark spots, fungus, or a different color. Also, an operator can manually check the percentage of debris, stones, hulls, and insect-damaged kernels. According to US standards, no more than 2% defective kernels per batch. It's mandatory to check how many kernels pop during a test heating. A good variety yields a minimum of 98% popping. After all checks, the kernels are cleaned, polished, and calibrated. They are often treated with special food additives or oils that improve texture, flavor, and shelf life. Popcorn comes in two main types: kernels for microwave or popcorn machines, and already popped, flavored, and packaged popcorn. The kernels are poured into heated drums, huge steel cylinders that rotate with a dull thud. Inside is dry air, heated to 450 degrees Fahrenheit. That's a temperature at which steel darkens and paper ignites in seconds. Hundreds of thousands of corn kernels continuously rotate, heating up from all sides. Inside each kernel, moisture gradually turns into steam, but it can't escape. The hard outer shell, which withstands incredible pressure, keeps it locked in like a miniature boiler. The tension builds, and then pop, pop, pop. The kernels burst with a characteristic sound that can be heard even through the drum casing. It's like fireworks, but instead of sparks, fluffy white popcorn snow that quickly fills the chamber. The moment a corn kernel explodes, its size increases by 40 or 50 times. It's literally a transformation, from a hard, shiny ball to a light, porous flour that immediately starts smelling like childhood, movie theaters, and salt. Everything happens in a flash. Each batch is ready in 2 minutes, and the drums work non-stop. The machine spits out hundreds of liters of hot popcorn, which immediately heads onto the flavoring stage. And this entire explosive performance is under complete control. Because what's at stake isn't just kernels, it's your perfect crunch. As soon as the corn clouds have popped in the drums, the next stage begins, creating that unforgettable flavor. Without it, popcorn is just crispy foam. With it, it's a caramel temptation, a cheesy sin, or a salty masterpiece. And it all happens on precise, computerized flavoring lines. A hot conveyor belt carries the popcorn to special coating drums where it gets its character. These drums are large, rotating cylinders with spray nozzles inside. Here, the popcorn tumbles around like on a carousel, and mixtures of salt, butter, caramel, or cheese powder are evenly sprayed under precise control of temperature and humidity. Popcorn arrives from the poppers or caramelizers hot. The temperature can reach 300 degrees Fahrenheit. To prevent kernels from sticking together and ensure crispness, the product is immediately sent onto conveyor belts or screens that are ventilated with cold air. The flow of cooling air is controlled by a computer that adjusts the temperature and speed according to the volume and type of popcorn. This allows a large batch of 500 or 1,000 pounds to cool down in 5 minutes without compromising its structure. When the popcorn reaches a temperature of about 77 degrees Fahrenheit, it is sent to automated packaging lines. It first passes through a sorting drum, where unpopped kernels and broken pieces are screened out. Only perfectly popped, light and airy kernels make it into the packaging machines. Depending on the product type, popcorn is packed into polypropylene or metallized bags, cardboard boxes, or large bags for bulk sale. Before sealing, an inert gas, usually nitrogen, is injected into the bags. This displaces oxygen, which slows down fat oxidation and extends shelf life up to 9 months without loss of quality. Then the packaging is hermetically sealed and marking is applied: manufacturing date, batch number, flavor, and ingredients. On average, one line can package 80 to 150 bags per minute, depending on size and weight. Cooled and packaged popcorn goes to palletizing and storage, or directly to distribution, to stores, movie theaters, or for online orders.